he's interested in the equine. I actually made notes before I came up here, but I left them in my office. Equine
Equine program director.
Okay,
Yeah.
Sorry about that.
No problem. So thanks so much for a Friday afternoon, and I know it's tough to schedule in the summer, so thanks. I really appreciate this. So I'm going to tell you today a little bit about basically who I am and my upbringing, my background, how I ended up working on racing surfaces, which is what I've been doing for now almost the last 20 years, thoroughbred racing surfaces. Talk a little bit about some of the mechanics associated with musculoskeletal disease, in particular laterality and the loading on the leg, and then some future work. This is something I ran across. This is the building I work in at the University of Maine, my lab and my office are in that. That's the old ag engineering building here at the University of Kentucky. I thought it was kind of entertaining. You know, you can certainly see the land grant tradition. They must have taken them off the template and putting them all over the country. So, about the same vintage building too. So I grew up in Leadville, Colorado. It's a molybdenum mining town. Everybody worked in the mine. I was the son of a mechanical engineer. He worked for the gas and electric utility. And he was a Colorado State graduate, so the land grant tradition, you know, the where he started. The only things I ever considered when I talked about a career was engineering and vet medicine. There was really, you know, nothing else. And I think it was partly, you know, going to land grant, you know, the kids who worked hard were in engineering and vet medicine, and that's who my dad introduced me to, and I knew I wasn't going to work in the mine. That was one of my personal goals. I went to General Motors Institute as an undergraduate and co-op in a spring and forge plant. That's the coil spring. You can see that the vet medicine was kind of overwhelmed by the mechanical engineering at that point in my life. And then grad school, I spent some time at Cornell, then went to Northwestern, worked at Electric Boat doing structural acoustics analysis for submarines. Then went to Yale, and then went back to Northwestern. The switching around from graduate schools, it had nothing to do with bad debts or a criminal record. It had to do with the woman who's now my wife and her educational schedule. So that's why I moved around. I then started as an assistant professor at Colorado State, where I was there for 5 years. The University of Maine, about 20 years ago, was given $10 million by the state to expand research in higher education. And the idea was to, basically the whole economy was going to be saved by research that came out of the university, and we all know the story, and it's either that narrative or the university is filled with people you don't like. But one narrative or the other seems to always kind of dominate, and that's when I moved to University of Maine. So that was a couple of years after that money was moved from the state government for research. And at that point I was able to expand my research program and do a lot of things, and I had cost share money, which as an assistant professor, cash cost share was king. So the academic side of it, I worked almost exclusively with ultrasonic testing early on. My master's degree was cracks in nickel alloys, the primary cooling loop in nuclear power plants. My PhD was reaction bonding in silicon nitride. It was a monitoring system for in situ monitoring, closed loop. Temperatures were incredibly high, like 1500 degrees C, 1800 degrees C I was working at. And then once I got a faculty position, I ended up doing two things. I ended up spending a lot of time on manufacturing-related processes, which looked more like what I'd done after I finished my undergraduate degree. And I worked a lot with natural materials. First thing I started working with was bones, imaging bones, and developing imaging techniques associated with that. I did some work with wood and some biofilms characterization. And then most recently, I ended up doing characterization for granular materials, especially high strain rate or moderate strain rate, not high strain rate. In general, since my background is in theoretical applied mechanics, these natural materials are great. I mean, they're anisotropic, they're nonlinear, you know, the constitutive relationships are interesting. You know, it's got all the complexity. But the other part of this is I really like problem solving. You know, I'm still a practical guy. And so if you start looking at these difficult materials in a practical sense, and it doesn't matter whether it's biofilm or wood or racetrack surface, there's all this difficult mechanics that gets built into it. But you got to practice. Somebody cares. You know, you get done, and you can immediately implement it and work with industry, and it's like they want the information. So it also is fun because it's interesting stuff. I mean, if you're going to work reaction bonding silicon nitride, sounds kind of cool. I'd much rather be at a racetrack, or I've also worked with horses and dogs and whales as well. So Here's the motivating work. 20 years ago, when I was at Colorado State, Chris Kalchek, who's the one there on the left, did his PhD in exercise-induced arthrosis, subchondral bone, and it was basically doing these training regimens on treadmills. So they did the training regimens, and my whole piece of this was looking at porosity versus mechanical behavior, and we had funding for waveguide-based acoustic microscopy. But it was 6 horses, 6 exercise horses, 6 control groups, and they exercised them on a treadmill. Now, anybody who knows anything about bones immediately thinks, why are you exercising on a treadmill? It's easy to control. It's not a physiologically representative surface. It's just weird. It's hard. So you've got a little mat. This was not any kind of fancy treadmill. This was just a normal horse treadmill. But it produced some very interesting results as far as bone remodeling mechanisms. All right. What I was doing was what we developed was a waveguide acoustic microscope. So using a waveguide, we were able to separate the signals in time. And what you're actually seeing overlapped on this is a high-resolution X-ray overlapped with the wave speed. So you're actually looking at the modulus versus that. There's a difference between the two of those that you can begin to look at the areas of bone remodeling where there was a high density of bone remodeling. Developing this then, after that, has been the primary thread of everything I've done with horses, because looking at this, it was high strain rate, or moderately high strain rate. Looking at the strain rate is what stimulates remodeling in the bone, and it was porous materials, which I've ended up doing a lot of work with. So, but the question that came up on here was the load rate of loading. So here they are, they're hitting this very hard surface. You've got a quite high rate of loading. So, what do you do next? The obvious next step on this is to get a more physiologically representative surface. So there's quite a bit to the mechanics of the hoof strike, because what happens is there's a primary and a secondary loading, and the impact of the hoof, that initial impact of the hoof before the fetlock rotates down, it's the center of mass of the horse is well behind the hoof. So it's really just the hoof coming down at high speed with very little mass associated with it. Then the center of mass of the horse moves forward, and that's when the fetlock's rotating down. When you see the fetlock rotating down, as the fetlock rotates down, then the center of mass of the horse is the secondary impact, where it's actually moving downward dynamically, rotating the fetlock, and you've got this spring damper system in the suspensory and bones, which is allowing it to provide this secondary loading. Peak loads are about 2.5 times body weight, that kind of range for a galloping horse. Jumping, they've seen as much as 3 times body weight. Interesting, it's the babies who do a crummy job and have the 3 or 4 times. It's the more experienced ones that end up at 2.5. Right, so we got this complex loading, and we know it's got to be strain rate dependent. So the only option on this is, if we're going to characterize surfaces, we have to replicate the loads and the speeds at impact. Because every one of these materials is strain rate dependent, every one of them is nonlinear, and so if you think about it, you can't do it with some sort of little object dropping it from a low speed. You have to replicate the entire speed of the system, you need to make the measurements, and then you can characterize it and compare it. So, the surfaces of interest, that's Kentucky Derby 2009, I think. So, the best known work that I've got so far is this biomechanical surfaces tester. It's a 2-axis loading system. It's all in the old public domain. There's one at Swedish University of Agriculture, California Horse Racing Board owns one, University of Central Lancashire has one. Anybody who does any development on it, they have to share with everybody else who's using it. Then I've got another system that I use, and actually Labosport in France is in the process of probably purchasing one as well from the machinist in Maine who built it. So the question then is, what are you measuring? Okay, so we replicated this thing. What do you use as baseline? There is nothing, right? Well, the baseline has got to be a safer track. So if you come in, and I come in and do my tests, the question is it a good track? Well, the answer has to be, it's got low catastrophic injury rates, the performance is good, it's easy to maintain, it doesn't vary from day to day. Okay, so how do we measure it's a good track? it's got to come back to epidemiology. So the epidemiology that drives it, and as we've developed this database, and this is what's happened for the last 15 years ago or so, we've gotten to the point now where we've got some measurements from a whole bunch of tracks. Now it's time to take it back. I still want to solve problems. We got to take it back to the horse again. So we really went from the horse to machine. Huge amount of data, something like 15,000 measurements in the United States alone on dirt tracks and 15,000 measurements on synthetic tracks. So it's representing using essentially the same protocol. We had some bumps in the road early on, but I guess that's not unusual. So really what we're doing is we're taking the epidemiology, and the next step is to tie this back to the Equine Entry database. So I don't know if any of you have heard of this, but being in Lexington, there's a chance that you would have, but the Jockey Club in 2008 launched a system where every horse that dies at the track within 72 hours of racing is logged to a central database. About 98% of this, well no, 92% of the starts in flat starts in the United States are going to the database, and almost 100% of the jump starts, which isn't that many, but about 100% of the, almost 100% of the jump starts go into the database. That's about 400 to 500,000 starts a year. If you take the baseline, there's about 3 catastrophic injuries per 1,000 starts. So that lives over at the Jockey Club. So really, that's the message, right? You're taking this, you've got this data, now we need to begin to correlate it to the outcomes, which would be the catastrophic injuries. So if we look at surfaces between 2009 and 2015, these are the sorts of numbers that we're looking at. Synthetic surfaces, like the old one that was at Keeneland, are about 1.22 catastrophic injuries per 1,000 starts. So again, this is horses that were euthanized within 72 hours of the race. It's just kind of the threshold. Turf is at 1.59 per 1,000 starts, and dirt's at 2.04 per 1,000 starts. That's too small to read, but the idea there is we've got some variation between years, and we had actually a very good year last year, which is probably completely unrelated to surfaces because the drop was on all surfaces. But the other take-home behind this is that the dirt tracks, the injury rates vary quite a bit between tracks between years. So we've got a higher injury rate on dirt here, but that's not across the board. So the real question is what's different with dirt tracks that would tend to be large variation in catastrophic injury rate from year to year, and a big variation between tracks. Well, this gives you an idea, and these are, this range is kind of understates it actually, this big variation between years on dirt, because these are several tracks, and these are actually quite good tracks. They're not labeled up there, but these are good tracks. These are not necessarily the bottom of the barrel sort of tracks. But if you look at synthetic, you see a lower level, but with the exception of Mr. Blue line there, you see very little variation between years. So that gives quite a bit of insight into maybe what's different. So what are the key differences? Well, if you know anything about synthetic racetrack surfaces, the biggest component difference is it's a high quartz content sand, it's the wood sand. It's mixed with fibrous rubber, and it's wax coated, so it's hydrophobic. Well, guess what? What in a soil or a sand surface would be the biggest variation you'd expect in the between year to year? It probably gets down to rainfall, okay? But the other thing that's really notable between those populations is a lot of small tracks are dirt as well, which means they have tighter radiuses, and you've got quite a bit of different dynamic on turning. If you look back, turf is not as safe as synthetic, and it's got quite a bit tighter radius because it's almost always inside the dirt track, with the exception of woodbine and downhill, of course, and Sand. So this gives an idea that maybe there's some mechanics in there that can be addressed, because what we really want to do, nobody's going to go back to synthetic surfaces. They could never go to synthetic surfaces in most places because it was a $10 million capital investment. Most racetracks can't do that. You know, so what the idea then is to go back and unbundle the issues that are associated with it. Okay, so let's talk about turning. So dirt tracks have more small radius turns. The material tends to move between harrowing and with rain, and it's probably a factor. And if we keep in mind that the whole goal of this is not so much just looking at this, but it's actually reducing musculoskeletal disease, this bone remodeling process that goes all the way back to what we learned with Chris Kalachek and other researchers' work in bone remodeling. So racetrack turns, okay, so if you were building a railroad track, this is some nice new research from 1890 on spiral turns, you know. So basically you gradually change your radius, you have the tight radius at the corner, you gradually change it, and then you can change your banking, right? You know how to do your banking because you start out with a large radius turn, you tighten the radius, the banking increases, then you just transition. Sounds great, right? What do racetracks look like? They have a constant radius turn, they're two circles, cut across spread, and you put two straight lines between them, and you got a racetrack. Why is that? Well, part of it has to do with maintenance, part of it has to do with tradition, part of it has to do with you're going to have a really complicated grading situation because you have to grade a dirt racetrack every day, and if you start having these spiral turns, it's not going to be simple. Okay, so then what do you say? How do we even figure out where to start the banking? Well, I mean, the physics would suggest that you go start the banking, full banking there, and you go all the way around the curve. Well, that's obviously not going to work. You know, you'd have to step up. Okay, so typical of anything that's kind of developed over history, there's actually two ways that banking is done in racetracks. Typically on the East Coast, what happens is the transition is in the curve. The peak banking is here. It doesn't start the banking until you start into the turn. So if you get a 1% crossfall in the straight, just to run so the water will run off, and you have 4% banking in the turn, that only means 4% at one point. 1% here, it just transitions through. If you look at it on the West Coast, what happens is they actually start 100 yards before the turn. They start their transition, and their transition is completed a quarter of the way into the turn. So there's some logic to that because it also has to do with the horse has a line that they're going to take. You know, you don't have to watch NASCAR for very long to realize that the line makes a big difference. So the assumption on this transition curve is that the horse is already pulled over to the rail, and the horses are essentially running on the rail by the time they're a quarter of the way through the turn. And as they get 3/4 of the way through the turn, they're already pulling out and getting the transition out. Okay. But there's no logic to where they're used. There's small tracks with big transitions because this should be a radius-related issue, but it's not. All right. I put this in here because this is a fun group because I don't have to explain this, but of course this is the centripetal force or the centripetal acceleration. We've got Newton's first law, the object in motion must remain in motion. We have the force, and so there's going to have to be a reaction force in order to turn the horse as it goes into the turn. All right, it's significant. If you got a 415-foot radius and you're at 40 miles an hour, you get 0.25 G acceleration. That's not negligible when you start looking at it. When you start looking at the entire horse, then you have to resist that force on those little tiny thoroughbred hooves. You know, those little tiny those have to produce that extra turning force as well as the propulsive force. So your dynamics between the hoof and the surface then become quite complex. So, and then of course keep in mind you got the weight of the horse. So if we take the 1,000 pounds, we got about 250 pounds. It's going laterally. So if you think about this, what would you expect? If you're turning like that, you'd expect to break a whole bunch of right leg, right? Makes perfect sense, right? You know? Well, data doesn't support it at all. Okay, physics isn't wrong. Okay, the physics is still okay, but you don't break a whole bunch of front legs. You know what you do? You break the left front and the right rear. Okay. All right. So physics is still intact, but we got to step back and do something else with the physics. Well, we can bank the track. Maybe that's the big factor there, right? How big a deal is banking of the track? Well, we don't have 25-degree banks, right? You know, those are the sorts of numbers. You know, it look like a velodrome, right? You know, a velodrome for bicycling. You know what those look like? That'd be the perfect banking. You know, on a velodrome, you don't steer a bicycle. You just ride it, right? Because it just goes up and you go up. And you go down, and you slow down, you move down, up, down. You can't do that. You're certainly not going to do that on a dirt track, because what's going to happen to your dirt? It's all going to be in the gutter at the bottom. Fair Hill Training Center in Maryland has 10% banking. Even a light rain, they have to cancel. They can't train on the track even at 10. So 10% isn't even an option. Okay, so this left, front, right, rear must have something else going on. Well, the horse is lean. So if you look at this whole thing and you assume a rigid body, everything falls apart, right? Because that's a significant factor there. When you can move your center of mass that far over, you're going to shift how things happen. How much do they lean? Well, we can look at the data, and we've got both kinematic measurements that we can make and kinetics, getting the force off the hooves. This may be a way to tie back to the physics a little bit. So, kinetic, one of the things that's been done recently by people with a huge resources is horseshoes. They take horseshoes and they put tracks, they load cells in shoes, they run. The problem is the shoes are heavy, so you can't gallop a horse. Okay, because once that, remember that passive thing where it's coming down initially? What happens is the whole motion initially is passive, and so your loading is changed quite dramatically by putting extra mass out there because the inertia. Well, keep in mind the horse is going 40 miles an hour. Well, so it's 35, conservative. 35 miles an hour. The foot's stationary part of the time. So that means during the swing phase, that hoof has to be going 70 miles an hour. Or you leave it behind, right? You got no option. So you can imagine these inertial effects down there at the end of a passive system. It's really got a spring damper system controlling it. No muscles controlling down there at the end. It's quite significant. You can also do force platforms. Well, that gets complicated. Can you imagine embedding a force platform, going over to Keeneland and telling him, don't bind us, we're just going to dig up this, you have to dig up the finish line. All right. We've also got the kinematics that we can do. This is Sarah Jane Cobbs, the professor in England who has the machine. This is something she did in a lunging ring where she actually changed the banking. Now again, the speed doesn't match the gallop that we're talking about, but it gets the same idea. Where we're going eventually with this is using inertial measurement units, scattering them all over the horse, and then you get the potential to actually run them on the surface because you'll have the full thing. But for now, what we've got is we've got pretty good data from what Sarah Jane did in England. And so you can see the banking that where Dr. Hobbs and her colleagues did the change the banking. So if you talk about the cannon bone, which is probably a good thing to think about, it's a nice long bone up there, something to look for. The inside forelimb is more inclined to the body, and the outside forelimb is less inclined to the body. And on the hind, they're similar to the body. Well, this begins to give some dynamics, so you can picture what's happening. But what's interesting to me is you've got this toppling moment. You've got two things you can do. You put a moment on each foot, right? You also have a couple that you can get out of the two by balancing the two loads. Our assumption in the right leg braking was that there was really that couple that was going to keep the horse from tipping over. But looking at this, they're moving it closer together. That has something to do with the dynamics of turning that suggests that there is the couple. Otherwise, you run them like this to try and maximize the distance. The lean of the rear cannon, hind cannon bones are similar to the body, so they're not doing anything back there to try. Okay? But these are significant even at low speed. So keep in mind, this is just in a lunging ring. This is not galloping on a thoroughbred or a racetrack. So in trying, they also move their head. Okay, now that makes sense. All right, you shift the center of mass. So what are we doing? There's all kinds of strategies that are used. Move everything inside. You get the center of mass. You can shift a lot of it right there. And this lean is significant even at low speeds. All right. All this is done in lunging, but in some ways racing is easier because you've got one job: go fast and gallop. Right? There's nobody thinking about it. You have to start. Stopping doesn't even matter because you do that after you already won or lost. So we need to explore the left side versus the right side. We need daily safety surface data for some key tracks to tie it back to these injuries, and then we can last the laterality, and then we can look at laterality of injuries. Okay. So this comes back to the equine injury database. We've got a natural experiment going on. We have everybody's turning left. They're all doing the same thing every day, right? They're doing it at maximum speed, assuming that there's nothing going on weird on the betting side of it, right? So what are they doing? Can the horse make its own banking? That's really the moment idea. Is the idea that the horse is actually creating a moment at the hooves. Is that the significant factor that allows them to turn? And then also look at this to the laterality of injuries, because obviously there's going to be some optimization of the surface that's going to go into the laterality of injuries if they're having to create their own banking with their hooves. So, bones act a lot like they obey Miner's rule. The difference with bones is they remodel. So Miner's rule, you get these overload opportunities and you're going to use them up one way or another. But in this case, what's happening is when you overload at this high strain rate, it's going to lay down more bone. So it gets a little more complicated how this is going to risk associated with laterality of injuries, because it probably has as much to do with training as it does with racing. Okay, so earlier we assumed the horse is a sphere. We know the horse is not a sphere. We always start with a spherical horse. Is that that's a punchline to physicists talking about cows and heat transfer, right? If any of you remember that joke. I don't, but yeah. But a horse is not a sphere. So, as we do with old Lagrangian formulation of the equations of motion, we take the motion of a point plus rotation of the horse, right? We separate the two as long as we use energy methods, we don't care. All right, so what rotates the horse? Well, if you're going to rotate the horse, you got to pull with the left, push with the back. Okay, this began to make sense with what we saw in the data. Now the question is, are we going to see something like that when we've got this natural experiment? We know which side they're turning. We know that there's a point moving around, and what happens? So the force, the lateral loading is to the outside. We need to produce the turning force and rotate the horse. There's going to be a moment in this direction, but then there's also going to be some sort of a twist happening as far as the hoof. All right, so here's some of the equine entry data that we have. Paper's in review now. What we have is we've got the left front limb, the left hind limb, the right hind limb, and the right front limb, and we got the probability. This is kind of a home run. You look at the p-values there, what happens? It's what's significant is the right versus left is significant only for dirt. This is really cool. When you start seeing laterality, this whole laterality disappearing because of the surface, going all the way back to that entry rate, I say, oh yeah, it's easy, it's water. Well, maybe it's not. Maybe it has to do with traction and the surface. Maybe all these injury rates differences are traction related and they have nothing to do with water. Well, they do have something to do with water because it's not going to be consistent. But this is an idea. It's like any other kind of a public health issue, and this is a public health issue because when a horse goes out there, it's not only the horse that's at risk, it's there's a rider on the back of every one of those horses. The most common source of catastrophic, significant injuries to the jockeys, which could be paralysis or death, is the horse breaking down. So it is a public health issue, and it's like any other public health issue. You get rid of one problem, and another one becomes your number one problem. But you can always work on number 2 or number 3 as you're working on number 1 because you know it's going to pop up. Okay, so if we look at trotting on the inside forelimb, we have abduction away from the midline and internal rotation moment at the foot. Exactly as you'd expect, pulling yourself around the corner. The outside is adduction to midline and large external rotation moment at the hook. I still don't understand some of this. I don't understand the mechanics and the words. As an engineer, I hate the abduction words for words. That's why I always have to have a picture up there. I can't even be a lateral level. And then what happens is the laterally positioned center of pressure is away from the midline. That makes sense. You're moving it away from the inside, away from the midline because you're digging into the outside. And then the medially positioned center of pressure towards the midline, you're moving it in. So you're cutting down into the surface to get around the corner. So it begins to make sense. So the hoof rotates, especially that end side one makes perfect sense, and then it cuts down in to get the horse around. So you can picture that moment. And it just basically creating its own banking. So turning is probably significant. So this is some research that was done a couple years ago, still isn't published yet. Jeff Thomason at Ontario Veterinary College, Wayne Maverick at Colorado State, and I did this work. It was with 9 thoroughbred horses in active training. Some of them have been retired, but they've been racing within 3 months. They were tested on separate days over the same sections of the racetrack at Woodbine in Toronto. The riders were familiar with the track, and they were actually the exercise riders who had been used by the trainer who had those horses. 5 evenly spaced strain rosettes were placed on each hoof around, and this is something Jeff's been doing since 1998. Now, of course, it's not calibrated. This is in the load cell. And the thing is, the hoof wall changes dramatically from the inside to the outside. But what it is if you use an internal control, which is really what we're talking about then, this turning, where you use left limb for the control for the right limb,